Hi, my name is Steve Dan with a company called Coto Technology. I'm going to talk to you today about some new magnetic sensors that we've developed. These are extremely small, extremely low power, high magnetic sensitivity devices. What I'm going to do actually is we've mounted a couple of these parts on a demonstration board that you can see here. And I'm going to go through some of the things you can do with these devices and show you some of their features and benefits. So here's our demo kit in close-up. Now what we've got on here, we've got one of the analog sensors, the RR110, that's at this end. And we've got one of the digital sensors, that's the 130 at this end. Every demo kit that we supply comes with this nifty neodymium magnet mounted with its north pole facing out. So if I bring that magnet up to the sensor, you can see that as the magnet gets closer and the field gets stronger, more bars light on the bar graph display. And when I move it away again, correspondingly, the bars fade. Now one bar corresponds to about 30 Gauss, and all the bars lit corresponds to about 60 Gauss. Now if I turn that around, I can do the same thing and demonstrate the use of the digital sensor. So you can see about 2 centimeters distance, the field's about 30 Gauss and the sensor turns on. Now I'm using a north pole here. This is what we call a unipolar sensor. It only responds to one particular pole of a magnet. That's not to say it won't work with a south pole as well. Here's a magnet mounted with its north pole facing out. As I bring that in, the sensor turns on. But I can get exactly the same effect by moving the south pole of the magnet towards the other side of the sensor. By the way, what we've done on this board is we've provided a switch which switches between off, on, and on with a beep. So let me show you. If I flip this switch over to this position and now approach the sensors with the magnet, when they turn on, you'll also hear an audible beep. The simplest RedRock sensor is the RedRock 110. It consists of a TMR element that, as we've discussed, changes its resistance in a magnetic field. Its response curve looks like this. The resistance changes from about 60 k ohms at zero field to about 30 k ohms at plus 100 Gauss. That's a north pole field. Note that there is little response to a negative field, in other words a south pole. However, a south pole pointed towards the other side of the sensor will produce the same shaped curve. The response on the steep linear portion of the response curve is about minus 500 ohms per Gauss. You'll see that the sensor saturates above about 100 Gauss and below 0 Gauss. The dynamic, in other words, the useful range of the sensor is about 20 to 90 Gauss, and the linear range is about 30 to 65 Gauss. To demonstrate the analog capabilities of the RedRock 110, we convert its resistance to voltage and then feed that through a display driver to an LED bar graph display. One green bar corresponds to about 25 Gauss, and all bars illuminated equals about 60 Gauss. For the RR120 digital sensor, instead of using the TMR sensor in analog mode, we pick off a single resistance corresponding to about 30 Gauss, convert to voltage and send it to a comparator and a latch that updates every 30 milliseconds. This circuit saves power since the RedRock 120 only turns on for a few microseconds every 30 milliseconds to take a reading from the TMR sensor. In fact, the average current consumed by the RR120 is only 350 nanoamps, thanks to the onboard CMOS circuitry built into the sensor. The existing RR120 operates at 30 milliseconds, equivalent to 33 Hz. Soon, higher speed versions operating at 100 Hz or 1500 Hz will also be available. In addition, higher sensitivity parts operating at under 10 Gauss will soon be available. The RR120 has a logic output that goes low when the sensor turns on. For higher power applications, the RedRock 130 adds an open drain MOSFET that can sink up to 15 milliamps. Another advantage of this configuration is that a source voltage higher than the VCC limit of 3.6 volts can be applied to Vout via a suitable pull-up resistor. This separate source voltage can be up to 6 volts. By the way, if you want to set VCC higher than 3.6 volts, Coto can recommend several ultra-low power voltage regulator chips that can accept up to a 20 volt supply. Now let's take a look at the angle at which the sensor can pick up the field from the magnet. The sensors are not particularly fussy about that angle. If you look at the way this small neodymium magnet's approaching the sensor, the principal axis of sensitivity is perpendicular to the actual package of the sensor, but I can bring that magnet in at different angles and still get a good response at maybe a slightly closer distance. Now the sensor also has some sensitivity in what we call a z-axis, the axis above the package. So if I bring a magnet in from this direction, you can also see that the sensor is activating with the north pole of that magnet. Now that can be important in some applications where you want to place the package on a circuit board and bring in a magnet from this direction. So it's useful to have that z-axis sensitivity feature. If we turn the demo board around so that we can present a magnet to the digital sensor, the 130, we should see exactly the same effects. Operation there. I bring the magnet around here, operation at 90 degrees that way, and also operation perpendicular to the package of the sensor that way. Okay, let me show you a few more applications here. I'm going to turn this back to the analog sensor, the 110. I showed you the standard magnet, cylindrical neodymium magnet that comes with the demonstration kit. But let me show you a different kind of magnet. This is a plastic bonded ferrite magnet. This is a magnet that's commonly used in level sensors. And let me show you why. If I take that ring magnet and move it slowly over the sensor, there's a very sharp operational point where the sensor turns on, and you can see that by all the bars lighting. This is an ideal kind of application such as level sensing, where you can imagine the ring magnet would be mounted on a float in some kind of fluid vessel like a brake fluid sensor, and as the magnet floats up and passes the sensor, which would be mounted on the axis of the ring magnet, the sensor turns on, indicating the level of the fluid in the reservoir. So to summarize, we've described Coto's new tunneling magnetoresistive sensors using our demo kit. We've seen the progression from a low-cost analog sensor, the RR110, to a digital sensor, the RR120, with its on-board power-saving CMOS circuitry, to a digital sensor, the RR130, with an onboard MOSFET switch capable of switching up to 15 milliamps. Already relatively small in a standard SOT23 package, the RedRock sensors will soon be available in an even smaller 1mm square package. These next generation sensors, available later this year, will have even lower average current consumption, about 200 nanoamps, and magnetic closure sensitivity options under 10 Gauss. And for applications that demand it, omnipolar sensors responding to either a north pole or a south pole are coming soon. For more information, go to our website, cotorelay.com, or send us an email at redrock@cotorelay.com. Thanks for watching.